There's a popular opinion out there that our theories of space, time, and matter will lead us to a physical theory of the mind. That opinion is a reminder of the definitions in Newton's Principia. Newton thought that the scientific and mathematical time and space was of the absolute nature. But the lessons of the 20th century were that the space, time, and matter we study in science are not absolute. The space, time, and matter of science are relative. Scientific theories are about relative reality and only relative reality, and they themselves are pieces of relative reality. It's all neatly contained. With paper and pencil using equations to directly describe relative space, time, and matter would have been the only conceivable option for physicists. But an entirely new way to apply mathematics to science may soon be possible. I conjecture that a computer has the ability to describe and predict relative space, time, and matter indirectly by modeling a mind in absolute space, time, and matter. Here's how we can make this a hypothesis. Step 1. Write a program to hypothetically represent absolute reality. The computer concept of objects in this program will represent something similar to, but not exactly like, particles, bosons, and quarks. And the rules of the program that determine its evolution will represent something similar to, but not exactly like, the fundamental forces and inertia. Step 2. The data of the program during its evolution represents a dynamic system. It should be made so a subsystem can interact with other subsystems in such a way that one subsystem has observed the other. Step 3. Decode the data of the observation. Whether we have to decipher it from a subsystem in the data so complex that it is similar to a neural network, or we can find a simpler method, extracting the encoded measurements of an internal observer would mean that a mathematical model of one ontology created another separate hypothetical ontology. The computer model will have modeled both absolute reality and relative reality. Step 4. Ignore the program's absolute data and focus on the abstracted results of the internal observation. Compare the computer's indirect predictions to our real observations of reality. Prediction 1. We model an observer with a photon source, a wall with 2 slits, and a wall behind that with a photon detector. Photon detectors may optionally be used on the slitted wall. The modeled observer doesn't have access to the program's absolute data. The modeled observer will only hear audible clicks from the detector. Despite the absolute data describing exactly where the photon is at all times, the modeled observations are the relevant data, and the modeled observations are the audible clicks from the detector. We will find the modeled observations match our real observations and demonstrate the uncertainty principle. Prediction 2. We model an observer and a metal rod traveling toward the observer. The rod is traveling at a velocity comparable to the velocity of the photons that actually allow for the observation. We will find that the observer's measurement of length are contracted in comparison to the program's absolute data, but the modeled observer's measurements will match what we see in reality. Conclusion. We will discover with mathematics that the natural process of observation itself is what creates our quantum and relativistic world. In the future, indirect predictions will become the standard way to model and understand the double slit experiment and length contraction. It will open up new territory to look for quantum gravity, and it will be accepted by science because of its ability to model and explain many diverse and complex phenomena starting from much simpler rules.